Yo, what's up guys? It's Brendan here. So, we all know basic symmetry, right? But do you know molecular symmetry? Come take a seat with me. Alright, so in order to fully understand molecular symmetry, there's a couple definitions we must go over. A symmetry operation is an action that leaves the molecule apparently unchanged in space. A symmetry element is the point, line, or plane in the molecule about which the symmetry operation occurs. In molecular symmetry, there are 5 basic symmetry elements that fully describe the symmetry of a molecule. Let's go take a look. So the first element is the simplest and easiest to understand. It's the identity element, represented with the symbol E. It exists in all molecules. There is no symmetric operation that is needed within these molecules, as this element basically just describes that there are molecules that are symmetric to one another in space and you can't distinguish between them. Now can you tell me what this is? It's a spoon. But how do you know it's a spoon? We know it's a spoon because it's symmetric to all other spoons that we've seen before. It's symmetric to this spoon as well. This shows how all molecules share the same identity element of E, as it has another molecule that it's symmetric with in space. The second element is the n-fold proper axis element, represented with the symbol C subscript n. With this element, we perform a rotation symmetry operation around an imaginary axis. The rotation is only qualified if the molecule is left unchanged in space. I'm sorry, I didn't quite catch you there. Yeah, so these headphones have a C2 element. If you were to imagine an imaginary axis going straight through the band of the headphones, we can rotate these 180 degrees. And they still appear unchanged. Pretty cool, huh? Instead of rotating 180 degrees, we can rotate 120 degrees and we'll have a C3 rotation element. Here, I have a vegetable spiralizer. If we rotate this 120 degrees, the spiralizer appears to stay unchanged in space. With this spiralizer, there are 3 variations. We have the C3, the C31, and the C32. If we rotate it one more time, we return back to the E element, or just the basic C3 rotation element. Here's a flower pot. In a 4-fold proper rotation, a C4, we rotate by 90 degrees each time. But be careful, rotating by 90 degrees twice results in rotating 180 degrees. And this describes a C2 rotation. With a C4 rotation, we have a C4, a C41, a C2, and a C43. So that's the n-fold proper rotation element. It's a rotation around an imaginary axis by 360 divided by n. The third element are mirror planes, represented by the symbol sigma. We will apply the reflection symmetry operation. There are 3 possible subscripts for the sigma reflection plane. There's the vertical, horizontal, and dihedral. Alright, so the vertical mirror plane is collinear with the principal rotation axis. So if we take the flower pot from the example before, we have our imaginary principal axis going straight down through the flower pot. If we take our mirror plane and have it collinear with that axis, we can see that it's even on both sides. The horizontal mirror plane is perpendicular to the principal rotation axis. So if we take our spiralizer from the demonstration beforehand, we can see that our principal rotation axis is down through the spiralizer, in which we can rotate it about. So if we bring our mirror plane and have it perpendicular, you can see that it's the same on either side. You can see that it's symmetrical. The dihedral mirror plane is also collinear with the principal rotation axis, just like the vertical mirror plane. But the difference, however, is that the dihedral mirror plane bisects as many bonds as possible, and the vertical mirror plane bisects as many atoms as possible.
What? Bro, what are you talking about, man?
If we take a look at our flower pot once again, but we have it turned upside down, and we imagine that the atoms are placed at each point of the flower pot base, we can see that this is a vertical mirror plane, as it is even on both sides. And this is a dihedral mirror plane, as it also is even on both sides. The fourth element is the n-fold improper axis element. It's represented with the symbol S subscript n. This element consists of both reflection and rotation operations. Here's world-class famous Chef Brendo to explain. Hello! Welcome to Brendo's Kitchen. Today, we're gonna make some gourmet fusilli. While we let our pasta cook, let me talk to you about the symmetry of the shape of the fusilli noodle. With the fusilli noodle, we are only going to focus on the top and the bottom of the noodle. We are going to totally disregard the spiral shape. With the fusilli noodle, we can notice that there are 3 points on the top and on the bottom of the noodle. These points are not in line with the other points on the other side of the noodle. We can then transfer this to making it look more like a molecule in space. I have now changed the fusilli noodle into more of a molecule that you would find in space. You can see that it has 3 tips on the bottom and on the top, and they are off-centered from each other. In an improper rotation element, we rotate the molecule so that the top portion of the molecule matches the bottom portion from before. So if we rotate it like this to match from before, we can now reflect it. By reflecting the molecule, it will result in the bottom portion of the molecule to come to the top and the top to go down to the bottom. If you were to reflect this molecule right now, it would result in a shape like this, which is exactly the same shape that we had before, showing that it does have an improper symmetry element. Returning back to the fusilli noodle, we can see that the points on the top and bottom are not aligned with each other. We can rotate it and reflect it, and the points will remain in the same place. However, you need to disregard the spiral shape as it will not reproduce the same spiral rotation. So yeah, the fusilli noodle has an improper rotation. The fifth and final element is the inversion center, represented with the symbol I. This element uses a center of inversion, which means that it's a point in the middle of a molecule. If you take every point on the molecule and push it through the center of inversion to the same distance on the other side, and the molecule still appears unchanged, that's a classification for a center of inversion. Brought to you by Vesper Theory. Hello everyone and welcome back to the 2020 Molecular Pool Tournament. There's the man of the hour, Photon Go Fast, in a race to the hill with electron density. But it seems as though Photon just has the upper hand as of right now. Let's see how this last shot goes. It seems as though Photon has great shape to make the 8 into the center pocket. What a quality game of pool we are having right now. Photon is grabbing the center inverted rake? How short is this guy? Oh yes! Welcome to... It's been a dream of mine ever since I was a kid. But it all came down to the center of inversion on this pool rake. Like, as you can see, if you take each point on the rake and move it down through the center from its original position to the same distance on the other side, the rake would appear unchanged, and just the rake helped me finish off the last ball on the table. I'm really happy with how I played, and it's been an honor for you guys to have me. So thank you so much.